Good morning, everyone. My name is Qiyang. Welcome to our UCLA OARC and IDRE workshops. Today, I would like to talk about learning PyTorch. This is our third talk in our Learning Deep Learning workshop series in this quarter. In this talk, I will first introduce what is PyTorch and why more and more people start using PyTorch for their deep learning projects. Next, I will present a couple of key components in PyTorch, including the tensors as the basic data blocks, and the autograd modules, optimized modules, and the neural network modules in PyTorch. In the third part of my talk, I would like to discuss PyTorch versus the other competitors in the deep learning frameworks, especially Tensorflow and JAX. I hope I can give you a little bit a bigger view on the subject and learn something new. So let's get us started. Let's first see what is PyTorch. As most of us already know that PyTorch is an open source Python-based deep learning framework. It was primarily developed by a research lab in Facebook named FAIR, F-A-I-R, as Facebook's AI Research Lab. I will review a brief history about the PyTorch in a short moment. But right in simple words, PyTorch can be understood as a replacement or re-implementation for NumPy. This replacement provides great support for various accelerators such as GPUs, ROCMs, TPUs, and not only for the NumPy, but also PyTorch provides a full set of deep learning libraries, including various neural network architectures, various optimizers, and various functions such as loss functions and other functions that define within the PyTorch. As its name indicates, PyTorch is from Torch. It is a 2002 project. So Torch is a group of internal libraries implemented by the C or CUDA. So they name it TH, means the first letter and last letter of the torch. And for the internal libraries, including the TH, THC, THNN, NN means neural networks, and also THCU and CU meaning CUDA-based neural network libraries. By that time, PyTorch began as an internship project at Facebook by a man named Adam Paskey, and gradually it got 2 more core developers on board and around 100 alpha testers from different companies and universities. Well, I have to say that at the same time, Facebook actually operates 2 main deep learning projects. One is PyTorch, the other one is what they call a convolutional architecture for fast feature embedding. That's what we know as Caffe, and they have the second version, they call it Caffe 2. A big movement happened in 2018 that Facebook merged those 2 projects into one. And technically, they actually moved the backend of the Caffe 2 into the PyTorch. And then the PyTorch became a major deep learning framework at Facebook. So this is the PyTorch 1.0. From then on, PyTorch keep updated frequently and actively. So as far as I know, the latest version of PyTorch is 1.10.0, was just released a couple of weeks ago. I mean, October 21st of 2021. It includes a lot of improvements in front-end API. For example, the module of torch.fx is moving to stable. Torch.special module becomes stable with gamma, Basel, and Gauss error functions, and more stable packages in distributed training, and a lot of improvements in performance optimization and the tooling in Torch script. In most cases, PyTorch are actually serving as backend building blocks in the deep learning software or deep learning applications. For example, if we open the Wikipedia for the PyTorch, it says there's a lot of bigger systems like a Tesla Autopilot, Uber's Pyro, and Hugging Face transformers using the PyTorch for their building blocks. Also, people developed a lot of like a higher level wrapper for the PyTorch, and they make the PyTorch usage looks more like a Keras. For example, like PyTorch Lightning, PyTorch Ignite, and Tensor layers, Fast.ai. Those are actually, we can think about a higher level of the PyTorch interfaces. At the same time, a lot of packages using the PyTorch for specific domains. For example, I list a couple of here, like NiftyTorch is for neuroimaging research built on top of the PyTorch, and Flare is the state-of-art natural language processing models built directly on PyTorch, and it has special support for biomedical data for named entity recognition. Scotch, that we mentioned in our previous talk, is a high-level PyTorch providing the full scikit-learn capability. ELF is a platform for game research, allow developers to train and test their algorithms in various game environments. And also like a Detectron 2 is a Facebook AI Research Lab's next generation platform for object detection and segmentation. So those are pretty much about the basic introduction for what is a PyTorch. And then we would like to ask why more and more people start using PyTorch. I would say that one of the major reasons is because of its simplicity. It is everything in PyTorch. It looks similar to NumPy, and everything of that is very Pythonic, and it integrates easily with the rest of Python ecosystems. And also, the APIs in PyTorch is fantastic. It's the design of APIs is very consistent from its early version to the latest version. So no significant changes. Compared to the PyTorch, the bad example is for the TensorFlow. It's notoriously bad for switching APIs so frequently, like from layers to Slim to estimators to tk.keras. In the TensorFlow, it introduced a great confusion among the users. So I think this is the strength for the PyTorch. The third reason why people using PyTorch, I would say it is because of its dynamic computer graphs. As we described in our backpropagation discussion in our previous deep learning mechanics talk, the neural networks can be looked at as a differentiable directed computer graphs. Here, the computer graph consists of nodes and edges. The edges can be either tensor or functions. The edges represent the dependencies or relationship between the nodes. In the PyTorch, the computer graph by default is a dynamic graph. Here, the word dynamic, I mean mainly three things. The one is the forward propagation is immediately executed. It refers as the eager mode, meaning there's no need to wait for the completion of the whole graph. Every line of code will dynamically add the computer nodes and edges defined by the run, and they will immediately go forward the propagation process to get the results. At the same time, whenever we want to doing the backpropagation, the backpropagation will be run by calling the backward method, or the gradient is calculated by torch.autograd.grad. And the third thing is that the computer graph will be eliminated immediately after the backpropagation to release the storage space. So remember, next time if we needed to call back, the PyTorch will need to reconstruct the computer graph. And if you calling the backward again, and you will get the error. The eager evaluation way is exceptionally good when we do the debugging or testing, since the Python interpreter, debugger, and similar tools have direct access to the Python objects, and we can get exceptions raised directly at the point where the issue occurs. Of course, on the other hand, the convenience from debugging and testing will bring some sacrifice on the performance. So for the production stage of work, the static graph mode always has won over the dynamic one, because in the static graph mode, it defers, it executes operations until later when the real input is passed. And actually, this is the default mode in Tensorflow 1.x. So right now, the trend is the major frameworks, especially for the PyTorch and the Tensorflow, are converging toward supporting both modes of operation. Started from version 1.0, PyTorch gained the ability to record the execution of a model into a static computation graph or define it through a precompiled scripting language, while at the same time, TensorFlow 2.x eager execution is enabled by default as well. To apply the trained model or algorithm to real applications, a big topic is in the inference stage. We would like to serialize and compress our model and later run, most likely outside of a Python environment. While most people always complain about PyTorch does not do a good job in the model deployment in real productions, and you can notice that the recent release notes from PyTorch are showing that PyTorch is making great progress in this part. And I think it makes PyTorch very promising and catching up with TensorFlow in the super fast pace. That actually forms my fourth reason of why people should try PyTorch. That is the model serialization and quantization. For example, by JIT, just-in-time compiler, you gain the ability to serialize your model and later run them outside of Python through libtorch. The libtorch is a C++ native module. This allows you to embed your deep learning models in various production environments like mobile or Internet of Things. PyTorch can also compile your JIT-enabled modules rather than running them as an interpreter, allowing for various optimizations and improving performance, both during training and inference. This is equally helpful for development and production stage. Torch script is an intermediate representation of a PyTorch model, so it can then be run in a high-performance environment such as C++. While to some extent we can understand that Torch script is a subset of Python, specified in details where, which, and when can be compiled by the PyTorch with just a few lines of torch.jet code and some simple model changes. You can export an asset that runs anywhere that libtorch does through either tracing or scripting way. FX is a toolkit for developers to use to transform NN.module instances for model quantizations. Quantization is a fairly recent technique for speeding up deep learning model inference time. Quantization refers to the techniques for performing computations and storing tensors at lower bit width than floating point precision. This technique has become very popular very quickly because it has been shown to provide impressive improvements in model performance in both research and production settings. Of course, the usage of those techniques and features will be far beyond the scope of today's talk. I'm just hoping that you can get a rough idea of the bigger picture. Next, we will continue our learning by diving into some basic components of the PyTorch. So let's first see the fundamental building blocks of data in PyTorch. Tensor. Tensor in PyTorch is the name for multi-dimensional array. In the array, it contains elements of a single data type. Right now, PyTorch defines 10 tensor types with CPU and GPU variants. It includes like 6 bits or 16 bits or 32 bits or 64 bits of integers or floating points, complex numbers, something like that. It is actually the same as the NumPy, but the different point is that in PyTorch Tensor, it does not support the string type. And generally speaking, the neural networks will commonly use torch.float32 type as the data. And we say multi-dimensional. It means, let's say, in the 0 dimension, we got a scalar number, and 1 dimension, we got a vector, and the 2 dimension, we got a matrix. And for the 3 dimensions, and we call it, usually we call it a tensor. And for the nth dimension, so I don't know how to represent it in the brackets, but it's something like we can understand as a different, what the number of indices we have, then we have the number dimensions of the tensor. In PyTorch, we don't use this way to represent the tensors. Instead, we use torch.tensor, this function, to create and represent the tensor. You can see that in this example, we create a 4-dimensional tensor. And the trick here is that the dimensionality of the tensor can be easily known from counting the number of the squared bracket at the beginning or at the end. To understand PyTorch tensor better, we may have to emphasize a clear distinction between the data for Python list and PyTorch tensors. As we know, a number in Python is not a simple piece of numeric value. It is actually a box as a full-fledged object. We call it py object with reference counting, of course. And Python list, or tuples of numbers, are collections of Python objects that are individually allocated in memory. Well, it will not be a problem for a small number of storing, but if we want to allocate millions of such numbers, things will get very inefficient. In contrast, PyTorch tensor or NumPy array arranged their numbers laying over a contiguous memory space. That space is just a compact pile of contiguous memory blocks. Each block contains unboxed C numeric types. Well, it means that if we have a 1-dimensional tensor of 1 million floating numbers, that will only require exactly 4 million contiguous bytes to be stored. A very important concept about tensors in PyTorch is that inside PyTorch, tensor is not only just a bunch of numbers stored in the memory, but also a chunk of header information associated on top of that numeric data. So they will have an overhead header information on that. Those headers form the metadata and provide the actual physical data information, such as physical size, the data types, and the device that the tensor will reside. At the same time, the metadata can define another layer of the logical view of the tensor, such as strides and offset. Those logical views can be understood as an index method to access the memory storage. For example, the size, or we use the NumPy's words like shape, is a tuple indicating how many elements across each dimension the tensor represents. By default, first index is for the rows, the second is for the columns. The offset is the index in the storage corresponding to the first element tensor. We show it up in this example, like 2.1 started with offset 1. The stride is the tuple indicating the number of elements in the storage that have to be skipped over to obtain the next element along each dimension. In PyTorch, if the stride number does not equal to 1, it means we will skip elements. By default, the stride will be the row measure, something like this, stride 3, 1. It means that for the next column, we will no skip element, but for the next row, we will skip the number of columns. To access the matrix, things become very easy because what we need to do is just to swap the stride from 1, 3, 1 to 1, 3. And it will make the access mode from row measure to column measure. Generally speaking, accessing an element ij in a two-dimensional tensor, it will as easy as to access the storage offset plus stride 1 index, first index of the stride times I plus the second index of the stride times j. The specific practical usage of tensors in PyTorch can be found in our Colab section accompanied with this workshop. You can simply visit this link and start the PyTorch code snippets on the fly. In this IPython notebook, we will see practical examples of all concepts introduced here, including the tensor-related operations like initialization and the NumPy interchangeability storage views and CUDA tensors, and also the automatic differentiation and the neural network projects that we will show in the later slides. If needed, I will record a separate video to go over all those details line by line. But right now, let's just focus on the slides presentation in this video. Before we move to the automatic differentiation module, I'd like to add a couple of more words generally about the tensor and PyTorch. What we discussed about tensor so far is the most commonly used layout type. I mean, it's a dense and strided tensors. In fact, for different domain tasks, there are other variants of layouts designed to be suitable for solving different problems, such as the sparse tensor, that is with the so-called coordinate format or COO format with the torch.sparse _COO _tensor, and the quantized tensors for storing quantized data represented as int8, uint8, or int32, along with quantization parameters like scale and 0 point. Encrypted tensors used in the framework for the privacy-preserving machine learning built on PyTorch named Crypton. And also some tensors to the layout specifically supporting for the MKLDN backend compiled to speed up the inference on some Intel-based CPUs. And also there are some XLA tensors. Those tensors are to support PyTorch running on XLA devices like TPU as we know, with the torch_SLA packages. In short, those tensors are all PyTorch tensors. They are just defined by different wrappers of different types of devices, design layouts, and the data types. Actually, as shown in the title of these slides, we should keep in mind that PyTorch has this PY part and the non-PY part together. All the above we talked about belongs to the Python part as PY, and the Python work is usually for the purpose of gluing and wrapping for the different pieces. And most of PyTorch actually is written in C++, C++, and CUDA. Those are doing the real heavy lifting work for the performance reasons. If you look into the internal architecture of PyTorch, we may find that we may need to do a lot of tasks to access the Python object through C and C++. that kind of work usually done by the Python extension objects in C, C++. For example, you may find an extra micro defined in the source code like a py_object_head to standardize Python objects and to expand to another structure that contains a pointer to a type object. Another two extra micro we may find in Python API is py_increref or py_decreref. Those are used to increment or decrement the reference counter of the Python object. From the official documentation for the PyTorch, we may found that the code base of PyTorch has almost like 4 components. One is the core Torch libraries, as we mentioned in our first slides about Torch. So it's related with the TH, THC, THN, THCUNN, and also some vendor libraries like CUDA, DNN, NCCL, and also some Python extension libraries, and also some additional third-party libraries like NumPy, MKL, LayPack, or DLPack, such and such. In most cases, we just install PyTorch by pip or conda install commands. We don't need to bother to know what kinds of internal structures inside the PyTorch source code. But just in case you are interested what it is, like myself, I like to list a couple of the most important folders under the PyTorch source code. At least, I think it would be helpful for us to know what and where exactly the Python and the C++ works together inside the PyTorch. One important folder is Torch. Torch contains the actual Python modules that you import and use. This stuff is the pure Python code and easy to hack in. Another subfolder is torch/C source code. This contains the C++ code that implements the front end of PyTorch. It has the binding code that translates between the Python and the C++ universe, and also some pretty important pieces of PyTorch like the autograd engine and the just-in-time JIT compiler. It also contains the C++ front-end code API. Another important folder or subfolder is A10. ATEN. This is a short name for A Tensor library. This is a C++ library that implements the operations of tensors. And the related one is the C10 folder. It contains the core abstractions of PyTorch, including the actual implementations of the tensor and the storage data structure. This weird name, C10, is a pun on Cafe 2 and A10. So that's what they named coming from. Next important part of PyTorch that we will talk about is automatic differentiation. Similar as the backpropagation is the central piece in the whole deep learning field, autograd package can be looked at as the central piece in PyTorch. It provides sort of a core engine connecting between the data and the models. As we mentioned about the backpropagation in our second deep learning workshop, during the model training, we need to compute the gradient of a composition of functions in the model and the loss with respect to their innermost parameters, W and B, by propagating derivatives backward using the chain rule. PyTorch implements tensors having the ability to remember where they come from in terms of the operations and the parent tensors that originated them. With the autograd package, given a forward expression, no matter how nested, they automatically provide the gradient of that expression with respect to its input parameter. It means that we don't need to derive our model by hand. It should be noted that the autograd package is not only for deep learning projects. It can be used in other scientific domains. especially the optimization problems. That is specifically meaningful in some newly emerged subjects right now, like differentiable physics or differentiable optimization problems. To run automatic differentiation in PyTorch is pretty simple. It just needs only 2 steps. The first step is to set tensors.requires underscore grad as true. Remember, by default, every tensor after creation and initialization sets requires underscore grad equals to false. By explicitly setting requires grad to be true, PyTorch will compute the derivatives of the loss throughout the chain of the functions, the computation graph, and accumulate their values in the grad attribute of those tensors, the leaf nodes of the graph. Each tensor has a dot grad underscore fn attribute that references a function that has created the tensor. The second step is just to call dot backward function. Calling backward will lead derivatives to accumulate at leaf nodes. Remember, by default, the dynamic graph will be destroyed when the backpropagation finished. So it means we should only call backward function once. Otherwise, calling backward immediately twice will report the error. In some cases, we would need to stop a tensor from tracking history. Generally speaking, the gradient accumulation is only expected in our training period. But in validation or testing stage, we do not want any accumulation of the gradients in a parameter tensor, because otherwise the training effectively happens on the whole dataset. So the better solution is to switch off the autograd whenever we don't need it. Of course, it has to be together with not calling backward anymore. The common method is to use the torch.no_grad context manager. We usually can see a lot of whiz blogs wrapping the validation and testing procedures. Sometimes tensors requires _grad is not set to false, even when created in a no-grad context. In that situation, it is best to manually use the detach function if we need to be sure. You can check a couple of code examples in our Colab demo file for all those function usages. I also add an example for using AutoGrad to solve an optimization problem, not a deep learning one. Another important package in PyTorch is torch.optim package. It implemented various optimization algorithms like stochastic gradient method and add method. To use torch.optim, you have to construct an optimizer object that will hold the current state and will update the parameters based on the computed gradients. The example that I shown here is that we define an optimizer with stochastic gradient methods passing the model parameters with a fixed learning rate and without momentum in this case. Generally speaking, you should make sure that optimized parameters live in consistent locations when optimizers are constructed and used. So let's say if we want to run a model to GPU, we need to move the model through .CUDA to GPU before constructing optimizer for it. Parameters of a model after .CUDA will be different objects with those before the call. When we do the training, we need to zero the gradient explicitly after using it for parameter updates. In PyTorch, we need to set the gradients to 0 manually before starting to do the backpropagation, because PyTorch accumulates the gradients on subsequent backward passes. So 0 underscore grad function, 0 the grad attributes for all parameters passed to the optimizer upon construction. Then what we need to do to update the parameters is to take an optimization step. That step means to call step function after the gradients are computed using the backward function. There are two ways to call it. One is just the step parenthesis. It is a simplified version supported by most optimizers, especially the gradient descent based methods. Some optimization algorithms, such as conjugated gradient or LBFGS, needed to re-evaluate the function multiple times, so you have to pass a closure that allows them to recompute your model. The closure should clear the gradients, compute the loss, and return it. In some cases, we may need to adjust the learning rate dynamically based on the number of epochs after the optimizer's update. Optim package provide learning rate scheduler to have several methods to allow dynamic learning rate in various ways. For example, it has a method named reduce LR on plateau, allows dynamic learning rate reducing based on some validation measurements. The detailed usage for those methods can be found in their official documentation site. Next, let's check another powerful package in PyTorch, probably the biggest one. It's a torch.nn package. This is the whole submodule with high-level APIs dedicated to neural networks. It contains all building blocks for neural network architectures. It uses tensors and automatic differentiation modules for training and building layers such as input, hidden, and output layers. NN package has two key modules. We usually use them a lot in our deep learning work. One is nn.functional. This module contains all functions in the torch.nn library, such as a wide range of loss and activation functions, some convenient functions for creating neural nets, such as pooling functions. The other one is nn.module. This one with uppercase M, different from the module in general Python. It is a PyTorch specific concept. It is a base class used to develop all neural network models. We can think of any PyTorch module as a Python class derived from the nn.module base class. For example, nn.module can manage model parameters by providing a class nn.parameter as subclass of tensors. We usually don't see nn.parameter or nn.parameter dictionary in the code because when tensors are used with modules as a model attribute, then it will automatically add it to the list of parameters. nn.module can also manage one or more submodules through subclassing nn.module. For example, nn.linear is a subclass of nn.module for a linear model or layer. The constructor to nn.linear accepts three arguments. Let's say the number of input features, the number of output features, and whether the linear model includes a bias or not. Roughly speaking, there are two ways to define a neural network. For simple networks, we can just concatenate modules through an nn.sequential container. A sequential object runs each of the modules contained within it in a sequential manner. This is a simpler way of writing our neural networks because we don't have to define the preferred method. In our Colab file, you will see a demo on defining a neural network with this method. If we want a model more complex than a simple sequence of pre-made or existing modules, we will need to define our model as a custom module subclass. Typically, we need to define two member functions inside the subclass. One is a constructor function. and assign the parameter or other pre-made modules like a ConvNet or customized one to self. We can also embed the containers as modules into the constructor, like the n.sequential or n.module list or n.module dictionary into that. The other member function in subclassing the n.module is a forward function, defining our module's computation by taking the input to the module and return the output. We don't need a backward function in the n.module because in the context of the standard torch operations, AutoGrad will take care of the backward pass automatically. We will see the module subclassing in our convolutional neural network talk. One note that we need to know specific in PyTorch is that the n.module expects the zeroth dimension of the input to be the number of samples in the batch. That means the input to the network has to be a tensor with the first index as the batch size. When we prepare the data input for the network, we usually need to pre-process the data to reshape it and reshape the tensor by unsqueeze function. We will see in our Colab demo, we will apply unsqueeze 1 with a dimension of size 1 inserted at the index 1 position on the tensor, converted from a NumPy array. A more systematic approach is to use PyTorch dataset and the data loader methods together. It will take care of the data index format and even batching shuffling of the data. For example, in dataset function, we can use torch.utils.data.tensor datasets to create the tensor-based dataset. Or we can use torchvision.datasets.image folder to create the image dataset according to the image folder. Or we can directly inherit torch.utils.data.dataset to define the customized datasets. For data loader, we can load the PyTorch's tensor-based dataset. It can control the size of batches, the sampling methods in batch, and wrap up the batch results in the model-needed format. We will illustrate the usage of the dataset plus data loader methods in our subsequent deep learning talks in winter quarter. As we mentioned above, n.functional provide a wide range of loss functions. Usually in PyTorch, those functions are converted in a form of class by subclassing n.module so that PyTorch can manage the parameters in a consistent way. And to make even more convenient, they were encapsulated directly under the n package. So we don't see n.functional, but directly see as n.lossfunction's name. For example, like n.MSE loss for regression problems, n.BCE loss for the binary classification problems, n.cross entropy loss for multi-class classification problems. An interesting note is that the parameter in loss function in PyTorch is different from the one in TensorFlow. In PyTorch, it assumes that the first parameter is the prediction value and the second parameter is the label with truth, while in TensorFlow it is the swap. An interesting note is that the parameter sequence in loss function in PyTorch is different from the one in TensorFlow. In PyTorch, it assumes that the first parameter is the prediction, and then the second is the label value with truth, while TensorFlow is the opposite. The truth label comes first, and then the prediction. At the end of this talk, I'd like to talk or summarize a little bit about the deep learning frameworks. In the last 2 years, the deep learning community largely consolidated behind either PyTorch or TensorFlow. A common sense right now is that PyTorch mostly dominates the academia due to its ease of use and rapid, consistent development. TensorFlow, on the other hand, dominates the industries because of its robust pipeline to production and an extensive industry-wide massive user base. During our discussion about PyTorch, we already mentioned about the TensorFlow here and there. Recently, there's a newcomer coming in the deep learning framework battles. It quickly draws people's attention. The name of the newcomer named JAX, JAX. I already mentioned it a little bit in my scikit-learn talk in the summer. JAX is a library by Google that was developed independently from TensorFlow. It can be considered as another version of NumPy recompiled using XLA and JIT on GPUs and TPUs. JAX implements great automatic differentiation and optimized to run on GPU, CPUs, and TPUs, specifically for high-performance machine learning research. According to my understanding from their official documents, JAX can be simply understood as having four major components. The first major component is the NumPy on accelerators. That pretty much is similar as the PyTorch and the TensorFlow has. And the second component is automatic differentiation from XLA. The full name of XLA is Accelerated Linear Algebra. It is a domain-specific compiler for linear algebra, originally from Google's TensorFlow. It provides an alternative mode of running models. Say, it compiles the neural network graph into a sequence of computation kernels and can accelerate neural net models with potentially no source code changes. It supports the grad function, forward mode differentiation, and back propagation, also known as reverse mode differentiation with arbitrary orders. It uses JIT for compilation of custom functions. Compilation and automatic differentiation can be composed arbitrarily to get maximum performance, all without leaving Python. The fourth major component is it uses function transformations like pmap or vmap to automatic parallelization and vectorization of the functions that can executed across different and multiple devices like GPUs and TPUs. I want to mention it specifically here because it has a great potential in the scientific physics-informed problems with its automatic differentiation ability. Although it is still very young, I personally believe and hope that this one, JAX, might have a very promising future in the deep learning field. So this ends our slides presentation. If you feel the contents of this talk is helpful, I would highly recommend to check our Colab demo for this session. It contains many practical examples and a lot of stuff that I didn't put in the slides. Please contact me or leave any comments below. Based on the requests and feedbacks, I might record the video clip to go over the Colab demo files as an accompaniment to this workshop. Thank you very much for listening. See you next quarter.